Hello students, so welcome all of you to the second live session of this course, Integral and Vector Calculus. So, in the question and answer sheet, I see that I have got 4 questions. So, the first question is, are you from MIT? So, no, I am not from MIT, and when you signed up, there was an introductory video about me, and it would have told you where I am from. So, actually my name is Shankar Mahato, and I am an assistant professor at the Indian Institute of Technology, Kharagpur. So, that is where I am working currently. Second question is how application in vector calculus in real life. So, the thing is there is a lot of application of vector calculus in real life. So, for example, if you study mechanics or fluid mechanics, continuum mechanics, most of the equations, they are derived using the concepts of vector calculus, and vector calculus is a very important concept to learn because for example, if you want to talk about the velocity of a fluid particle, there the velocity, as you know, it has a magnitude as well as it is it's basically a vector, and you do need vectors to represent the velocity of a fluid particle, or to talk about its acceleration, and if you want to derive some equations of motion, say Navier-Stokes equation, Euler's equation, any type of equations that originate from fluid mechanics or continuum mechanics, there you need the concepts of vector calculus, not only mechanics, but in general it is a very important subject to study. So, I would say it is a very important topic, and you all should pay good attention to it. Third question is, why are we studying integrals? Because first of all, integral calculus gives you an idea that the functions which you are dealing with, if you want to, let us say, calculate, so first if we talk about the definite integral. So, definite integral are nothing but we calculate the area bounded between a curve and two endpoints. So, x equals to a and x equals to b, if these are the two points of the interval within which you are calculating the area bounded by a curve y equals to f x. So, basically you calculate it using the formula integral from a to b f x dx. So, that is where one of the applications of definite integral, because you cannot have all the time square and triangle or nicely looking curves for which we know the formula for area. Let us say in case of rectangle, its length into breadth, but if you have any curve, then in that case those formulas, they will no longer work. So, that is one such application of integrals. Integrals are also helpful when you are studying a deeper concepts of functional analysis. So, there you have inequalities like Holder's inequality, Minkowski's inequality. So, they usually come from Lebesgue integral and all that how to say topics, but it is a continuous process. So, basically in your +2 level you study about Newtonian integral, where you have everything very nicely behaving functions which are continuous, differentiable, and it is relatively easy to perform the integral. Then as you progress, you learn about Riemann integral, where the functions can be also discontinuous, but you can still be able to do the calculate the integral. Then you learn about Lebesgue integral, where the function are only Lebesgue measurable, and so on. So, integral calculus plays a very important role, and you must study, I would say. Fourth question is, kindly describe about your course. So, if you have looked at the introductory video, there I have explained the entire course structure and why it is necessary. It is the very basic course for the BTech students. You have to know integral calculus, vector calculus in order to start studying any branches of engineering or mathematics. So, these are the basic courses that lay the foundation of your further studies. So, integral and vector calculus, these are very basic. Besides this, you have to study several other topics like linear algebra, then differential calculus, differential equations, transform calculus. So, this is just one of the, how to say, many important topics that you have to study before you can start working on any one of your B.Tech degrees or graduation degrees. So, it is actually an important course. So, these are the 4 questions that were given by the students. So, now I am going to go back to the live session. There I will see how many questions have been posted by the students. So far I do not see any questions posted by anyone. So, if you have any questions or queries, I am here for the next 1 hour. So, you can ask me and I will try. So, I see one more question, one question posted by some student. The question is in itself incomplete. So, you have to post a proper question for me to understand what you are actually asking. I believe you want to know Bessel functions application. So, since this course does not include anything about Bessel functions, I would rather not talk about it. However, if you are interested, why do we need to study Bessel functions, you can look for series solution of second order differential equations, and there you will be able to find how Bessel functions originated and where are they applicable. But for the time being, since this course does not cover that topic, I would rather not discuss about it. All right. So, I can see one more question which says explain how we parameterize surface. So, first of all, when you are trying to parameterize any given let us say curve or a surface, uh, what usually it means is that you need to introduce a parameter which you can vary over a certain interval, and with the help of which you can be able to generate all the points that are going to lie on that particular curve. So, for example, we can start with let us say a circle x square plus y square equals to a square. So, this is a circle centered at origin and radius a, and then when you actually draw the circle, basically we can see what are the points that are lying on the on this particular curve. So, for example, a comma 0 or minus a comma 0 or 0 comma a and 0 comma minus a. So, for example, these 4 points, they lie on the surface of the circle. So, similarly, there are like infinitely many points that are lying on this circle, and if you want to generate, let us say, all those points by using a certain kind of parameterization. So, your parametric equation must be able to generate all those points that are lying on the circle, and when you eliminate that parameter, then it will give you the curve back. So, for example, in this case, if you have a circle, you can write x equals to a cos t and y equals to a sin t. So, when you are summing up x square plus y square, then in that case you are getting a square. So, you are getting your curve back, and since you have one complete round, that means the circle is like one complete round. So, when you are varying your t from 0 to 2 pi, then it is making one complete round. So, then your range for the parameter t is between 0 to 2 pi, and your parametric equation is x equals to a cos t and y equals to a sin t. Now, for every value of t between 0 to 2 pi, you can be able to generate all the points. I mean, you can be able to generate one particular point, of course, lying on that circle. So, for example, when you take t equals to 0, then you will have x equals to, if I have said a cos t, then in that case x will be a, and y equals to a sin t. So, sin 0 is 0. So, y will be 0. So, then in that case a comma 0. So, when t is 0, then the point which you are getting on the circle is a comma 0. Similarly, you can take now t equals to pi by 2. So, then your cos will be 0 and sin will be a. So, then it will give you the point lying on the y axis, and similarly you can alter all the values of t, and that will give you the points lying on the circle. So, that is how you parameterize. You introduce a parameter which is varying on a certain range, so that you can be able to generate all the points for that particular curve or a surface. You can have let us say a sphere in 3D given by x square plus y square plus z square equals to a square, and if you want to write its parametric representation, so then in that case you introduce let us say if you are writing in spherical polar coordinate system. So, then in that case you write x equals to a cos theta cos phi, y equals to a cos theta sin phi, and z equals to a sin theta, where a is the radius and theta will run between 0 to 2 pi, phi will run between 0 to pi, or vice versa. So, I have to actually calculate for the ranges for theta and phi, but one of them will be between 0 to 2 pi and another one will be between 0 to pi. Now, based on which you can generate all the points lying on that sphere. So, that is another parametric that is one of the parametric representation for the sphere, and that is how we introduce the parameterization. I believe whenever you are generating a parametric representation, it is usually you introduce a parameter, one parameter or two parameter, with the help of which you can try to write the curve or the given surface. So, it depends on the context, in which context we are talking about. If we are given a circle, parabola, ellipse, based on which you write down the parametric representation, and if you are in 3D, then it is a sphere, paraboloid, ellipsoid, based on which you can also write the parametric representation for them, and that's how it is done. Yes, I just explained that how to parameterize even a 3D surface. So, a sphere is a 3D surface, and in that case you might need two parameters. So, for example, in case of x square plus y square plus z square equals to a square. So, if you want to parameterize it, you write x equals to a cos theta cos phi, y equals to a cos theta sin phi, and z equals to a sin theta. So, here theta and phi are the two parameters, and your a is basically constant. And depending on the ranges for theta and phi, you alter the value of theta and phi, and that will give you the points, all the points on the surface of the sphere. So, depending on whether you are talking about a 2D structure or 3D structure, the number of parameters would also increase. Okay, and one more question is, I think it is by the same student, how parameterization help in calculating surface integral. So, parameterization, so it is hard to say where to use the parameterization and where to not. So, it entirely depends on the given problem. So, suppose some problems where you have the given integrand in such a way that if you substitute some values of x, y and z, then it will reduce into a very simpler integral. Let us say you substituted spherical, you substituted for x, y and z in spherical polar coordinate system, and everything reduced to calculating the integral of dr, d theta and d phi, which is relatively simple than calculating some difficult or some complicated x, y, z expression. So, it entirely depends on the given problem. Sometimes it is helpful to do the substitution. So, there is really no rule of thumb that I can tell you that okay, in this situation use the parametric representation, and in this situation you do not have to. It usually comes with the how to say practice. So, you have to practice a lot of problems, so that when you see a certain problem where you need to make some substitution so that it can be reduced into a simpler integral, I would suggest you can do that. Otherwise, you can proceed with the usual method of projection, and then you calculate if you are projecting on let us say xy plane. So, based on which you can calculate that normal, and then you calculate the surface integral what we have studied. But in some cases parameterization does reduce some efforts. So, that usually comes with the practice. Okay, some student is asking me about please explain vector space. So, since vector space is not in the syllabus of this particular course, I cannot talk about vector space. So, if you are interested to know about vector space, you have to look into a linear algebra book. Usually, it means that you have a non-empty set which is complemented with two compositions, usual addition and multiplication, and then it satisfies 10 properties, which you can find in any linear algebra book if you look at the definition of vector space. And if it satisfies all those 10 properties, you can be able to say that it is a vector space. Now, based on the vector space, you have whole lot of theory. So, for example, linear transformation, then matrix theory, then dimension, cardinal, several. I mean, it's a whole new topic, and I mean, in itself, it's a very vast topic. So, I cannot simply explain vector space in a 2-minute explanation. So, if you are interested, you should look into any linear algebra book. Now, what we are studying here in the vector calculus and the vector spaces, which you have asked, they are two different. In some way, some of the examples might be connected, but the theories and the topics which you will learn in these two subjects are entirely different. So, which book is best for vector calculus? I don't know which book is best. So, whichever book you find where you can see these topics. So, I have already taught you, and you have the video lectures on NPTEL forum. There I have also given the references, for example, the books where you can look into. So, I have already suggested you the books, and now that you know the topic, you can just look for the books which contains those topics and just read from there. Because there is no one best book that I can recommend. So, I usually consult at least 4 or 5 books before I go and teach something. So, it is hard for me to pinpoint this particular book is best. So, someone has asked how surface integral and volume integral is same in divergence theorem. I am not getting this point. So, I cannot. So, first of all, if you talk about Gauss divergence theorem, so there usually it is saying that you can convert a surface integral into a volume integral. Now, that does not mean that you are saying that surface integral is in a way same as volume integral. I mean, what we are basically saying is that you are, with the help of Gauss divergence theorem, when you are given a surface integral based on certain properties of the function, you can write that surface integral equals to a volume integral. So, if you calculate the value of the surface integral using the usual formula for calculating the surface integral, like taking the projection and then calculating the normal and then putting it into the usual formula, and if you calculate the divergence of the given vector function and then you calculate the volume integral, both the values will be same. If you look at the expression, so one of them is the double integral, another one is the triple integral. Not only that, the integrand within the integral are different. So, they are not, you know, when we are saying that the value is same, that does not mean that here you have surface integral. So, on the right hand side where we are doing the volume integral, there also we have double integral. No, there is a triple integral, and at the same time the divergence, I mean the integrand is different. Here you just have a surface integral, there you have divergence of f. So, basically what Gauss divergence theorem says that if you have a vector function which satisfies some properties, I am sure I have given the statement, then based on which you can be able to convert the given surface integral into a volume integral. Now, that conversion has some proof, but if you look at the integrand, then the integrand for the surface integral is different, integrand for the volume integral is different. So, that is how it is different, the value is same. All right. Next question is I cannot feel of gradient, divergence and curl. So, basically in differential calculus for the function of one variable, we had a dy dx. So, you were given a function of x, and if you were asked to calculate the rate of change of that function. So, basically what you did is you did df dx or dy dx. If you are given a function of two variable, then basically since your function is varying along x axis, I mean since it has two variables along x axis and y axis. So, we cannot simply talk about dy dx, because now in this case there is no dy dx, because you will also have a component of in a way derivative along y direction as well. So, if you are doing df dx, then you must also do df dy, but then again you cannot have two total derivatives. So, what you can have is the partial derivative. So, you have del f del x and del f del y, and based on which you can calculate the total differential, which for which you have already studied the formula. So, in case of vector calculus now, if you want to vector calculus, I mean basically vectors have three directions, and at least if you are in 3D, then it has three directions. And if we say that we have a vector function, let us say, then a vector function has R3 to R3, and then in that case if you are talking about the rate of change of the function along x axis or y axis or z axis, then it is not as simple as function of scalar functions, right. So, then if that means it does not have any other components, it has only one component, and it is a mapping from R3 to R. So, when you charge your nabla operator, which is a vector, on a scalar, that is when it is called as gradient, and that gradient is a normal to the given surface f x y z equals to c. So, if f x y z equals to c is the given surface in 3-dimensional space, then gradient of f will be a normal to the surface f, and we basically calculate del f del x I, del f del y j, del f del z k. So, that is how we calculate the gradient of a given vector function f. Now, if you charge the gradient nabla operator on a vector function. So, basically charging that nabla operator, which is a vector, on again a vector function will be done in two ways. So, either you can do it a dot product or you can do a cross product. So, when you are doing a dot product, so what will happen is you will simply write nabla dot f, and then since f is a vector, nabla is a vector. So, you will end up having del f del x plus del f del y, del f 1 del x, del f plus del f 2 del y plus del f 3 del z, because your function f, which is a vector function, may have three components f 1, f 2, f 3. If you are charging the given nabla operator on a function f, which is a vector function, via cross product, then that is when it is called as curl. So, if it is if the charging of the operator nabla is done via dot product, then it is called as divergence. If it is done via cross product, then it is called as curl. And based on divergence, gradient and curl, there are a lot of equations in applied mathematics that can be derived. For example, if you have a chemical transport in a porous medium, so there usually the chemical species they diffuse inside the pore space of the given porous medium, and that diffusion will be written as a gradient of the concentration. So, that is one such application, and there are several other places where you can apply the concepts of divergence, gradient and curl. Okay, one more. I think it's a suggestion that please teach complex analysis in next session. So usually, it's. I think there are a lot of other NPTEL videos that are available and courses on complex analysis. So you find about them on NPTEL forum. Since my research expertise are differential equations, partial differential equations, applied analysis, mathematical modeling. So usually I may not get a chance to teach complex analysis. So I usually get possibility of teaching subjects that are closer to my research area, closer to my expertise, and I think for complex analysis there are several other faculties who are more than qualified than me to teach complex analysis. So and about them you can be able to find out on NPTEL forum, and I have seen and I'm pretty sure there will be a lot of helpful video lectures on NPTEL itself. I might propose the course on mathematical modeling. So in the next session, when they will ask about possible courses, I will make a proposal regarding mathematical modeling, and if it gets approved, I might try to teach that. But so far, let's limit ourselves to questions on the integral and vector calculus. So here the next question is the difference between free vector and vector passed through a point. So first of all, if you have a vector passing through a point, that usually doesn't make sense, because a vector itself, let's say if you have a 2i plus 3j plus 4k, then basically you have a point 2, 3, 4 and origin, and then you connect this OP vector that is given by 2i plus 3j plus 4k. So when you say a vector passing through a point, it usually means that you have a vector function, because even in case of function of one variable or function of two variable, when you say that a certain curve or a surface passing through a point, then you basically had a function of x, y and z, or function of x simply. So here a vector passing through a point doesn't make any sense. So you have to have vector function, and when it passes through a certain point, that means it usually satisfies that vector equation in a way. So if you study vector algebra, there you will be able to write the equation of a plane, vector plane basically, and there we talk about certain vector planes passing through a point and things like that. Now, a difference between free vector. Now, free vector is usually I don't know in what context you are referring this term free vector. But free vector is something in a way you can treat it as a constant vector, which doesn't depend on any parameter, or which if you have a vector equation, when you integrate it, then that constant vector can be treated as a free vector. But it also depends on in which context you are talking about. So randomly, it's a little bit hard for me to explain that what is free vector here. Another question is what is curl and divergence. So I just explained what is curl and divergence like a few minutes ago. So when you charge the nabla operator, which is a vector operator, on a given vector function, then that charging will be done either via dot product or cross product, because you have a vector and you are putting another vector on top of it. So that can be done only via two operations that so far we know that works in case of vectors, dot product and cross product. So when you are taking the dot product, that is when you have divergence. When you are taking the cross product, that is when you have curl. All right. One more question is, what is mapping of vectors? So again, you have to write the question in detail, but mapping of vectors, I don't know what do you mean by it, whether it is a mapping of one vector to another vector, or simply vectors that are vector functions that are defined as a map from R3 to R3. So for example, if you have let us say f x y z equals to f1I plus f2j plus f3k, where each f1, f2, f3 are some functions of x, y and z, then that is a mapping from R3 to R3. Now mapping of a vector to another vector, that is something I also have to see. I mean, what do we mean by that mapping of a vector? But usually vector functions, they map R3 to R3. Now mapping of one vector to another vector, so one student is asking mapping of one vector to another vector. So if you have a vector, let us say, I know you can map, you can treat that vector as a point. So for example, when I am saying that a vector function is a mapping from R3 to R3, so even in R3, if you choose any point, let us say 2, 3, 4, then in that case that can be written as 2y plus 3j plus 4k. And instead of taking that vector, you can take it as a point 2, 3, 4, and then you substitute in your given vector function, which will give you another vector. So that way, I mean, it's the same thing what I just explained, that when you are saying mapping of vectors, it basically you treat any vector in R3 as a point and x, y, z, and with the help of which you write your vector function. That is how you define this mapping of vectors, which you defined. So, I believe we ran out of time for today's live session. So, I tried to answer all of your questions as much as I could, and I will be available for next live session next month. So, if you have any questions, you can write on the forum, or you can ask them in the next session, in the next live session. So, see you in the next session.